In this video, we'll be covering section 10.2, the parabola. We have three objectives. We will be analyzing parabolas with their vertex at the origin. We will then analyze parabolas that are shifted. Their vertex will be at some point, which we'll refer to as HK. And then we will finish this off with looking at applied problems involving parabolas. So in the previous section, we defined a parabola as a conic section. We said that if you take a plane and slice it so that it's parallel to the sides of the cone, that the cross-section created would be a parabola. But in this section, we want to give a purely geometric definition. We're going to define it as what's called a locus of points, meaning a set of points that have a certain property to them. So this definition says that a parabola is the collection of all points P in a plane that are the same distance d away from a fixed point F as they are from a fixed line D. So that's a lot of words. Let's come over to this picture. So the idea is to create a parabola, you need two things. You need a focus, a point F, and a given line D, which we're calling the directrix. The parabola will be the set of all points in the plane that are the same distance away from the point F as they are from the line itself, from D. They are equidistant to this red line and this point F. Every single point over here, if I just picked a random point, if I were to measure this distance to the point F and the distance to the line, which would have to be a perpendicular segment, those would be congruent no matter where you're at. At any place, pick any single point on the parabola, this perpendicular segment would have to be the same as the distance to the focus. So that's a purely geometric definition for a parabola. So you could denote this in set builder form. Over here we said it's the set of all points P such that the distance between F and P is equal to the distance between P and the directrix. So in this section we're going to be using this notation, this kind of like a function notation to denote distance. Okay, so suppose we have a parabola and we have a directrix and we have the focus. Then we're going to define the axis of symmetry, this line here, to be the line that passes through the focus and is perpendicular to the directrix. You can see that that does divide the parabola in half. It is symmetric about that line. Now there will be a point that the axis of symmetry intersects. That point will be called the vertex of the parabola. And it's the same point that we called a vertex back in algebra as well. It's going to be the lowest point or the highest point, depending on how it's oriented for that graph. So for us, though, we're defining it to be where the axis of symmetry intersects the parabola. We're then going to define the distance from the vertex to the focus. This segment here, we're going to say that its length is A, just denoting that distance with A. Now remember that every point on a parabola is the same distance away from the focus as it is from the directrix. So if this segment is A, then this segment here would also have to be A. They're both going to be equal to each other. So the total distance from the focus to the directrix would always be 2A. Okay, so what we want to do is come up with an equation for a parabola in general. And we're going to start with the type of parabola that is opening sideways like this. So let's assume for now that the vertex is at the origin. This is going to be an assumption we stick with for a little while here. And let's also assume that the focus is at the point A0. So remember, we've already said that the distance from the vertex to the focus is defined to be A, so this coordinate makes sense. And we also know that the distance here is also A. If this is at the origin, then this point right here would have to be negative A, 0. So that means that the directrix would have to pass through that point, and so the directrix would have to have the equation x equals negative A in this type of figure. So we can go ahead and fill that in over here. Our directrix would have to be x equals negative A. Remember that the directrix, it's not just a number, it's an equation of a line. Okay, so let's find some distances. We know that the distance from P to the directrix, this segment here, is always equal to the distance from P to the focus. But let's start with this segment. So we want an expression that represents the length of that. Well, since it's a horizontal line, all we have to do is look at the difference in their x-coordinates. The x-coordinate of this point is going to be negative a, and the x-coordinate here is obviously just x. So we could write that distance down as the absolute value of x minus negative a. Right, we're just taking the difference in their x-coordinates. So that could be simplified down to x, or absolute value of x plus a. So that will represent the length of this segment. The only reason we have the absolute values here is that in our picture we are assuming that x is on the right side, but we could also reverse this and this formula would still work if the parabola were over here, let's say. Okay, now let's go back and do the distance from the focus to this point P. So to do that, we will just use the distance formula. So that means we're going to do the difference in the x's. The x coordinate will start with P actually. It'd be x minus a all squared, difference in the x's, plus the differences in the y's, so y minus 0 all squared. That can be simplified down to the square root of x minus a squared plus y squared. Okay, now since it is a parabola, that means those two segments have to be equal. This segment has to be equal to that segment, which means we can set those two distances equal to each other. Then all we have to do is try to simplify this and we'll get the equation we're looking for. So let's square both sides. If I square the side on the left, I can just write this as x plus a quantity squared. I can drop the absolute values because squaring it would wipe out any negatives. When I square this side, I'll have x minus a all squared plus y squared. Just cancels out the square root. Now we should expand each of these. Just FOIL them. So we'll have x squared plus 2ax plus a squared from the left side. On the right side, we will get x squared minus 2ax plus a squared and plus a y squared back here. Okay, so then we get some cancellation. So notice we can cancel the x squareds on both sides. We can cancel the a squareds on both sides. Then, if we move this to the other side, we can add the negative 2ax over, and you get 4ax equals y squared. This is our general equation for a parabola that is opening to the right, like you see here with the vertex at the origin. We will just typically reverse it. Y squared equals 4ax. Remember, a represents the distance from the vertex to the focus. So if you know this distance, you can just plug it directly in here and you have your equation. So this is giving us that exact same formula. Anytime it's opening up on the right, then the distance from the vertex to the focus is just a, and that a gets multiplied by 4. I'm not sure about this fact, but I think that this is where the term quadratic probably comes from, the fact that there's a 4 here for any parabola that you see. Now, using the exact same argument, we could go through the same math and we would get an equation, a similar equation for a parabola that is opening vertically. So you can see it's the exact same structure. The previous one was y squared equals 4ax. This one is x squared equals 4ay. And again, a still represents the distance from the vertex to the focus. So the exact same relationship. Okay, now when we're graphing these parabolas, it's going to be handy to use to be able to find two other points. And to easily be able to find two other points, we use what is called the latus rectum. Yes, I know it has a funny name, but this comes from Latin and it just means right. So lattice would be a side. This is a side, I guess, that is maybe at a right angle with the axis of symmetry. I'm not sure why they chose this term, but so latus rectum, what it is it's simply the segment that it's perpendicular to the axis and it passes through the focus. And it turns out that in any quadratic, or any parabola I should say, that this is a, and then the each piece here that you see is 2a. So if you know how long this is, you can move over twice that to find 2 other points. That also tells you that the total distance here, obviously, is 4a's. Right, the length of the lattice rectum is 4 times this distance. And that's true no matter if it's opening to the right or if it's opening vertically. So the main reason we will use this, or the main purpose for this, will be to help us draw graphs. Okay, so let's try writing an equation. So we are given that the vertex is at the origin. So let's go ahead and plot that. For right now, all of our vertices will be at the origin. The focus is at the point 3, 0. So I do think when you're doing these, it's helpful to label them. Now, given that this tells us that the axis of symmetry is the x-axis itself here, which means that our parabola is going to have to be opening sideways like this. So that immediately tells us that the equation we want is the y-squared form. So this is going to be y² equals 4ax. All we have to do is figure out what the a is. Well, the a is just the distance here. So in this problem, a is 3. So we can immediately write our formula. Y² equals, it will be 12x. So that gives us the formula for this, but it also asks us to graph it. Okay, so to graph it, we should use the lattice rectum. So the lattice rectum says that if this is 3, then we need to go up twice that and down twice that. So we're going to go up 6 units to get another point, and go down 6 units to get another point. So that this entire segment should be 4 times. It's 12 units long. Then that gives us 3 points, so we should be able to just connect those. And please forgive how bad this is going to look. All right, so that gives us the graph of the rough graph of the parabola. But let's go ahead and write down some other information. For example, the directrix. So the directrix is the same distance away from the focus as the focus is from the vertex. So we just need to go back 3 units and draw a vertical line down through here. And that would be our directrix D. So D is the equation x equals -3. So remember, the definition of the parabola is that every single point on this curve should be the same distance away from F as it is from D. Let's move on to our next one. Okay, so on this one, they gave us the equation. We need to find the vertex, we need to find the focus, and the directrix, and then graph it. So we can clearly see that this has the form y² equals 4ax. So we have an 8 here. That means 8 must equal 4a. So a is obviously 2. Anytime your equation is in this form, we know that the vertex is the origin. All right, this is always the form of a parabola with the vertex at the origin. So we know that that was basically just given immediately. Okay, so then now that we have a, we can figure out where the focus is. It's got to be 2 units away. So if this was v, this would have to be the focus. So focus has the coordinates of 2, 0. We also know that the directrix is the same distance away from the vertex as the focus is. It's just in the reverse direction. So the directrix has to be coming back here. So I'm actually going to use the line tool just to be able to draw that a little faster. So that would be D. Oops. So our directrix is given by the equation x equals -2. All right, so we have those 3 things. Now we just need to finish the graph, so we need 2 additional points. So this is where we use the lattice rectum. We know that this is 2 units, which means the lattice rectum is 4 times that. So we just need to go up twice as much as this and go down twice as much. So this is 2 units. If I go up twice that, it'll be up 4 and down 4. And that gives us our 3 points. Notice the entire length of this is 4 times the distance from the vertex to the focus. So basically the same type of graph as before. These are all going to look very similar to each other. We're just basically changing the scale for the distance from the vertex to the focus each time. Now, both of our examples open to the right. It is possible for them to open to the left, and that simply happens when A is negative, or if you just see a negative out in front of this. So that's all that these images are indicating. If you had, for example, x squared equals negative 18y, well, that tells you your picture is going to look something like this. It's going to be frowning. You can see that is consistent with what we would have done back in algebra. When we were graphing these in algebra, we always would have it solved for y. So if we did solve this for y, you'd have y equals negative 1 over 18 x squared. And we know just from transformations of functions that this negative would be flipping it vertically. So it is still consistent with what we would have done in a previous course. So let's try one of those. Okay, first thing to notice, this has the form x squared equals 4ay, which tells us that it's opening vertically, so it's either smiling or it's frowning. And the fact that this is negative tells us that it is frowning. So let's start by finding the a. So we know 4a is equal to negative 12, so a is obviously negative 3. Since the equation is in this form, this immediately tells us that the vertex is the origin. Everything we've done so far, the vertex has been at the origin, so we already know that. And so let's plot it. So there's V, and we know A is negative 3. So the first thing to recognize is we're frowning on this one. So the focus has to be down here, and it's going to be 3 units away from the vertex. So it would be here. This would be our focus. And then our directrix is going to be on the opposite side, so it would be up here at positive 3. So that is going to be the directrix. So we can label focus was 0, negative 3, and directrix is x equal 3. All right, so we got vertex, we have the focus, we have the directrix, so now we just need to finish the graph. So to finish the graph, we need the other 2 points. This is where the lattice rectum comes in. So this distance here is 3, which means we need to move 6 units to the right and 6 units to the left. We double it on each side, or think of it as multiply that by 4, so this is a total of 12 units long. And then we're just connecting. And that gives us our graph. Okay, let's move on to the next one. Okay, in this example, we were given some slightly different information. It says, find the equation of the parabola with the focus at 0, 4, and the directrix is the line y equals negative 4. So let's go ahead and plot the focus. Focus is here at 0, 4, and the directrix is a horizontal line down here, y equals negative 4. So let's label this as F. We know that the vertex has to be halfway between the directrix and the focus, right? Every point on the parabola, the vertex is a point on the parabola, is equidistant between the focus and the vertex. Or sorry, focus and the directrix. So right there, 0, 0, like every problem, that has to be our focus. Or sorry, vertex. Now the other thing we can tell from this is that the parabola is going to have to be opening up. Right, given the way the directrix is drawn here, we have to open this direction. So the equation, the form that we would use would be the x squared equals 4ay. Since it is opening vertically, it has to be the x squared form. We also know that this distance here is the a. So the a value is, be careful with the scale here, a value is actually 4. So all we need to do is plug this in and we have our equation. So x squared equals 4 times 4y, or x squared equals 16y. So there's our equation. That's all they actually asked for, but let's go ahead and finish the graph. So we know that to get the other 2 points, we need to move horizontally twice the distance of A. So since A was 4, we're going to have to move 8 on the left and 8 on the right. Or you can also just think of this number here is always the length of the lattice rectum, which is 16 units in this case. And then connect your points. And didn't quite make it on that one, but that would be our graph. Okay, example 5. It says, find the equation of the parabola with the vertex 0, 0 if its axis of symmetry is the x-axis and the graph contains the point -1/2, 2. We're going to find its focus, directrix, and then also graph the equation. Okay, so let's plot the vertex as 0, 0. And we know that it passes through the point -1/2, 2. So go back a half, up 2. So it passes through this. Okay, and then it says the axis of symmetry is the x-axis. So let's put that in there. I'm going to use a different color for that. Now, don't get confused here. That red line is the axis of symmetry, right? This is not the directrix. So the axis of symmetry actually has to cut it in half. So given the points that we have right now, we know that the parabola is going to have to go through a path like this. It's opening horizontally, which tells us that we know the equation is y squared equals 4ax, because it's opening up horizontally like this. So we just need to figure out the a. Well, the way to get the a is to use this point. This is an x value and that's a y value that has to satisfy this equation. So we just plug all of that in. So 2 squared has to equal 4 times a times -1/2. And we just solved this for a. So 4 equals -2a. When I multiply the -1/2 and the 4, divide over, a equals -2. So then we can get our equation by just plugging this back in. So we end up with y squared equals -8. X is our equation of that parabola. Okay, but they asked us to find the focus, so let's do that. So focus, we know that if this is the vertex, then we're going to be moving to the left because a is negative here. We would move 2 units. So right there should be our focus. So focus is the point 0 or -2, 0. We want the directrix. So the directrix is an equation of a line. It should be the same distance away from the vertex as the focus is. So it's going to be back here. So that equation is x equals 2. All right, and then it says to graph it. So to finish the graph, we need 2 additional points. So we know that if this distance is 2, then this distance should be 4. So we go up 4 and down 4. Or you can think of the total length of that segment has to be this number here, at least the absolute value of that number. And then we can actually get a symmetric point from this one. There would have to be one on the same place on the other side. And then you just connect them. And that gives us our graph. Now keep in mind, this directrix is not technically part of the graph. It really should probably be put in as a dotted line, but I don't have a convenient way of doing that right now. I mean, I could come back and do this, I guess. So that would be a better looking graph. Okay, so all of the examples up to this point have had a vertex at the origin. But now we want to look at moving the vertex. So we've actually seen this type of procedure before. Back when we studied circles in geometry, we started off with the equation of a circle centered at the origin. And that was the equation of a circle centered at the origin. Then we shifted this. We moved it to a different center. And that equation turned into x minus h squared plus y minus k squared equals r squared. The center for that circle was the point hk. So the idea was, if you were going to move it h units to the right, you subtracted h from the x. If you were going to move it up k units, then you subtracted k from the y. The same exact procedure works for a parabola. So if we look at the example of a parabola opening vertically, this was the equation. And if we're going to move the vertex right now is 0, 0, just like the center for this was 0, 0. If I want to move it h units to the right and then k units up, we replace the x by x minus h, and we replace the y by y minus k in the exact same way that we did for a circle. So really the equation has the same structure, it's just that the vertex has transformed it, has moved it either left or right, depending on whether it's positive or negative. Okay, so the figure you see down below is just illustrating what those equations look like in each of the cases, but they really are all the same thing. They're all describing exactly the same thing. So the big thing you have to be careful with is the k value is always going to go with the y, and the h is always going to go with the x. So they kind of get reversed in these two forms. And then the other thing that we have to be careful with is there's always these built-in minus signs in those formulas. And that's usually where we have the issues, is that people want to have them switched around. So let's see an example with these. Okay, this says find the equation of the parabola with the vertex at -2, 3, and the focus is at 0, 3. So let's plot that. Vertex back 2 up 3, and focus is 0, 3. These are the ones where it's really critical, I think, for you to label, because you can easily get it messed up or get it backwards if you don't have them labeled. Okay, so the distance here between them is the a value, so we immediately know a is 2. And we could also draw in the directrix. So the directrix is on the, like the vertex is the midpoint between the focus and the directrix. So the directrix has to be back here. Let's try that again. So this is what I mean by being very careful about the way you're labeling these, is that if you had them backwards, you would have put the directrix on this side. But just remember, vertex is always halfway between the focus and the directrix. So if we're going to write the equation of that down, didn't actually ask for it, but the directrix would be x equals -4. Okay, so the next thing to notice is, since the directrix is running vertical, we're going to have to open horizontally like this, which means the equation that we're going to be using is the y minus k squared equals 4a times x minus h, that form. All right, it's the y squared form, we just now have the h and the k in there. So we know that the vertex is the point hk. So in this problem, we know h is actually -2 and k is 3. So we have everything we need now. We just need to put all of this information into that formula. So we end up with y minus 3 squared equals 8 times x plus 2. Notice I'm putting the -2 in for the h, so that's why we end up with a plus here. And that's it. Right, that is the equation of that line. Okay, or that parabola. Now let's graph it. So just as before, we go to the focus, and we're going to move twice a vertically and up and down. So we're going to go up 4 units from where we're currently at. So that's going to take us up to 7, and then move down 4 units, which should take us here, and then connect those points. And that gives us our graph. Okay, next example says find the vertex, focus, and directrix for this parabola. And I know you're saying, well, man, that does not look like a parabola at all. Currently, it does not. Our goal is going to be to put this in the form of x minus h squared equals 4 times a times y, y minus, sorry, k. So I know it's this form because the only one that's squared is x. If the y was squared, it would be the other form. So somehow we have to translate it into this form. What that means is we need to get a perfect square here. So what we're going to do is move the y to the other side, and we're going to complete the square. We're going to add something here so that we get a perfect square. Now we have to remember that whatever we add on the left side, we have to add to the right side as well. Okay, so it's been a little while since we completed the square, so hopefully you're all remembering that to complete the square, you take this b term, that coefficient we call b, we take half of it, and then we square it. That is the thing that we have to add to both sides. So for this problem, that's going to be 4 over 2 squared, which is 2 squared, which is 4 again. Now it is just a coincidence that what we're adding is the same as this coefficient. Most of the time it will not be the same. Okay, so we've added that on both sides. So now this should factor as a perfect square. And it does, it's x plus 2 squared. On the right hand side, these are not like terms, but what we need is we need to factor this out. In other words, we need the coefficient of y to be 1. So no matter what is in front of the y, it has to be factored out. So if we factor the 4 out, we are left with just y plus 1. So now you can see they do have the exact same form. We can see that a has to be 1 because 4 has to equal 4a, so the a would be 1. We also know that the vertex, which is the point hk, well, in this problem, h is -2, and k would be -1. Right, be careful here. Remember, there's supposed to be a minus sign, and since we don't see minus here, the h actually has to be -2. That's how we end up getting the plus sign there. Okay, so this gives us enough to start graphing things. So we've got the vertex is -2, -1. So back 2, down 1. That is vertex. We know also that this thing is smiling. It's opening up like this because we're squared, or sorry, x is squared, and the a is a positive number. So we have to be opening vertically. So that means our focus is going to be, we have to move up to get there. And the a tells us how far up to move, which is just going to take us right there. So that's our focus. That also tells us our directrix is down 1 unit. So this line would be the directrix. And let's go ahead and write these down, I guess, since it is asking for it. We already got the vertex written down. Focus is the point -2, 0, and directrix is the horizontal line y equal -2. Okay, then to get our other points, we go to the focus and we move 2 times a to the right, so we're going to move over 2 units and move to the left 2 units. Right, the a value is 1, so we just go 2 units to the right, 2 units to the left. And then connect your points. And that gives us the graph. We got the vertex, we've got the focus, and the directrix, so we have answered all of it. Okay, let's try one more of these. So this is not in the book, but I just thought it'd be useful to see at least one more example of this. So this one, notice, is y squared, which tells us we're opening horizontally. We're either going to open to the left or we're going to open to the right. We'll see after we find the a value. So just like the previous one, we want to move everything that doesn't have a y over to the right-hand side. So this will give us y squared minus 6y plus, I'm going to leave a blank, equals -12x minus 69 plus a blank. So again, we figure out what we add by doing b over 2 squared, and 6 is the b value on this one. So it'll be 6 over 2 squared, that's 3 squared. So we're going to do, looks like we're adding 9 on both sides. Okay, so that gives us, on the left-hand side, that's a perfect square now. So that'll be x minus 3 squared. So notice technically I should have put -6 in here, but the square wiped the negative out. However, when you factor it, this sign is always going to match the sign that you see here. Right? It's the positive comes from the fact that -3 times -3 is still +9. Okay, and then over here you have -12x minus 60. So then, just like before, whatever is in front of this variable, it gets factored out. So we end up with that. Okay, so from this, we know that this should be equal to 4a. Right? The general equation that we're using here is y minus k squared equals 4a times x minus h. So -12 has to equal 4a, so a is going to be -3. We also know that the vertex is the point hk, and the h always comes from the x, so be careful, it's not always over here, it comes from the x. So on this one it is -5, and then the k is a +3. And then also be careful with the signs. It's a built-in negative sign, which is why I'm using -5, and I'm using a +3 because that negative is part of the formula. Okay, so let's go ahead and graph the vertex. So we go 5 to the left and then up 3. That is our vertex. Since it is a y-squared problem, we know that it's going to be opening horizontally, and the a is negative, which means it's going to be opening to the left. So we're going this direction here. So our focus has to be to the left of the vertex. The focus is always inside, and if our parabola is opening like this, that means the focus is going to be in here. And it's 3 units away, so we move 3 units to the left to get to that focus. So that puts us here at -8. So the focus is -8, +3. And directrix, then, we can go ahead and put that in. It's going to be vertical, and it should be 3 units back from the vertex. So directrix has the equation x equals -2. All right, so we have those 3 things that it asked for. Now we just need to finish the graph. So to finish the graph, go to your focus, and we're going to do 2 times the value of a, which means we got to go up 6 units and down 6 units, since the a value was 3, or -3. So that's going to take us up to, it looks like 9, and then take us down to -3 here. And then we can connect those points, hopefully. All right, and that gives us our graph. Again, directrix should probably be drawn as a dashed line. Okay, so last thing we want to look at are applied problems using parabolas. So why do we care about parabolas at all? Well, parabolas have a really important property, and that property is if you imagine the parabola representing some kind of a boundary, some kind of a surface, let's say, and I think the easy example is to think of it as the reflective coating on a flashlight or any kind of a beam. If you place a light bulb at the focus of the vertex, the light from the light bulb will shoot out in straight lines in lots of different directions, but it will shoot out in straight lines. And so when that light comes out of the light bulb, it will strike the reflective surface. And there's a geometric property for parabolas that when it hits that surface, it will be bounced off in a line that is parallel to the axis of symmetry for the parabola, right? The axis of symmetry would run through here. So every beam of light that comes out of that point will be reflected in parallel lines. Right? This is why a flashlight shoots light out in a beam like that. So this is the important property for a parabola, and it works in both directions. So that means suppose you have something moving towards this parabolic surface. So the example that's usually given is something like a satellite dish. So we've got radio waves coming in, and usually they're moving in parallel lines like this. So if the radio waves are all coming in, they're going to strike the surface of the satellite, and they're going to be bounced into the focus. And this is why when you see a satellite dish, it has some kind of a receiver in the center, some kind of arm, some boom put out, and then out in the middle of that, that would be the focus generated by that parabola. Now, obviously, satellites and flashlights, they're three-dimensional. So what you do is you get what's called a paraboloid by taking this curve and rotating it about this central axis. So you get this dish that you see here. This is a paraboloid. So definitely a very useful feature for a parabola. Not every curve has that property. In the notes, I have a little section devoted to proving why this actually has to be true. I'm not going to put you through that right now, but I will encourage you to read that. It uses some good old geometry that we did back a couple of years ago, things that we hopefully still remember. So I'll let you read through that at your own pleasure. Let's look at an actual example. Okay, so it says a satellite dish is shaped like a paraboloid of revolution. So that's just a parabola rotated about that central axis, meaning if you took a cross section through it, each cross section there is a parabola. Okay, it says the signals that emanate from a satellite strike the surface of the dish and are reflected to a single point where the receiver is located. The point where it's reflected is the focus. So we would say right here, that point would be the focus of the satellite dish. That's where everything is bounced into. It says if the dish is 8 feet across at its opening and 3 feet deep at its center, what position should the receiver be placed? In other words, where should the focus be? Okay, so to model this problem, we've got our paraboloid here. It's 8 feet in diameter and 3 feet deep. So what I've done is I've embedded this in a coordinate axis. I have it opening vertically, but you could solve the same problem opening horizontally as well. So since it is opening vertically, I know that the equation we're going to use is the x squared form. So it would be x squared equals 4ay. And notice I've placed it so the vertex is at the origin, which is why I don't have to use the h and the k. Now, since it's 8 feet wide, that means that the x values for each of these points would be 4 and -4, and 3 feet high, we're going to have 3 for each of the y values. So all we have to do is figure out what the a value is, and we can just use one of these points to get that. Just take the point, plug it in, and solve for a. So this gives us, if we put 4 in for the x and 3 in for the y, then we have 16 is equal to 12a, and then all we have to do is divide over, so a comes out to 16 over 12. If we reduce that, they're both divisible by 4, so it's 4/3. So the focus is the point 0, 4/3. Right, remember that the distance between the focus and the vertex, that distance is just a. So as soon as we find a, we can put it in here, and that gives us the point. So that means that we should put the receiver about 1 1/3 foot out from the center of that dish. All right, and that's that. I think that's our last example. So hopefully this made sense. If you have questions, make sure you're emailing me, and we'll see you guys on the next video.